name is Behnke. I'm from the University of Applied Sciences in Hamburg, in cooperation with the University of the West of Scotland. I was told to say this in good pronunciation. I'll be telling you a little bit about QuP. It is an acronym, or it was at one point. Its meaning is lost, so just take it as a proper noun. Before I go into what QuP does and how it does it, I'll want to give you an idea on why I felt necessary to build something like that. The idea grew out of the project Timodoros. It's the simple and little idea to build a new type of MMORPG that has some things and supports some modes of operation that are not seen today. One is there shall be no shards and no zones. I hope everybody in this audience is familiar with a shard and a zone is, and if not, just we have the perfect talk yesterday that shows us all. Also, this is a service. This is something that's supposed to be cloud-based, or whatever cloud is. Anyway, we should at some point in the future get 5 nines of uptime, including planned downtime. Why can't we have an RPG service that is as good as the phone service? It should be resistant to cheating. No cheating. Everything's either not possible because it's prohibited by the server, or it's possible, and if you want to do it, it's allowed. What is allowed and what not is a question to the game designer, but the system should support enforcing these decisions. Now, in the top row, you see that it's supposed to support more than 10,000 users. I know that's a huge number compared to what we have today, but my vision is to support modes of operation like fighting the Battle of Helm's Deep, where you're being Gandalf is kind of pointless, but let's say you're one of the orc leaders and you have 100 guys following you, your commands, all in real time, and if you mess up, your guys will mess up, and the orc's going to lose the battle still. Other things are the Metaverse. That's a virtual amusement park, or a district of a major city, or a Rolling Stones concert. We have thousands of fans screaming in one direction. All these types of very large crowds with most of the time limited real interaction with totally everybody are what QuP is supposed to support within Project Timodoros. Okay, how to do it? Well, QuP basically forms a classic three-layer architecture. We have clients with either a native client or some browser connecting to a server layer, and the server layer instead, in turn, propagates the global state of the virtual environment to a storage layer. We handle Nimbus and Aura-based area of interest management. As has been published before, there's nothing there, but we do make, or we draw some assumptions from this basic idea that the dependency of objects is in close spatial proximity. All your buddies are around you within a couple of 100 feet, and the fact that there is some guy in white standing up on the hill is nice. You want to see him, but what he does in detail and his discussion with this other guy next to him is not really that interesting. Visibility range is limited within this space. You can, due to all the other orcs around you, not see very far. And that is not so much true for Helm's Clam. Most of the objects that you can see around you are passive objects, just objects, and not avatars or NPCs moving around. All these assumptions only need to be valid in the majority. If there are some active objects and a lot of passive objects, that's fine. The way QuP does this is place everything in the spatial volume of the whole virtual environment into an octree. I've chosen a quad tree here just for display purposes. And the objects are placed in the smallest node that will fully encompass the bounding box or the nimbus of an object. So smaller objects go down further into the tree. Because of that, by selecting subtrees, I can achieve an overestimating heuristic of the area of interest by placing a virtual object or a meta object as the observer point for the view region into the tree according to the same rules as the placement of the actual object. And from these observer points, I add up envelopes of a server. Every object in the subtree that contains the observer points of all the clients connected to that server form this envelope. The positions within the trees are automatically updated as the observer, or as the object, and thus the observer moves around. It can also be moved up or down if the area of interest, or the view area, the sight distance, whatever, changes, possibly due to game design rules or reasons of load management. Now, why all this walking around in the bug tree? Basically, this QuP tries to do very aggressive preloading and caching, and you have a single object cache per game server that caches the whole subtree as would be possibly required for accessing or doing reads on objects for each of the connected clients. The idea here being that in a hypothetical static state, all the necessary information that a client could, in theory, access by looking around is already loaded onto the server that the client is connected to. Of course, this is probably will never happen in completeness while the game's running, while people are running around and continuously updating the state. Now, the title of the talk says resilient propagation. The resiliency part comes in through the structuring of the storage layer. It is strongly derived from the Dynamo system that was published in 2007. That's the key value storage that Amazon uses throughout. And it basically does a consistent hashing, or implements a consistent hashing where you have segments of a key space assigned to this ring. The key space is just the SHA-1 hash namespace, and each storage server assign or registers a number of these segments with the game servers so that all changes are written out to these servers. Now, there is not only one server written for each change, but the consecutive n for n type or n level redundancy. And changes, transactions going out receive an answer upon which quorum is created in order to ensure that the redundancy was, or that the information was redundant. The quorum may be sloppy. Currently it is not. At the moment we use just a straight quorum. Everybody has to answer. As the installations go bigger, that will probably not be sustainable, but that's a point of further study. All objects and all nodes are just identified by bit string IDs, And as far as the storage layer is concerned, there's no difference to it. They just have a number and some values. Okay, how does it handle failure? First of all, the server only holds the ephemeral state. It can do all the calculations at once, it can do all the caching at once, but if it dies, just restart it. At the worst, the clients have to be reconnected. Reconnecting clients is part of the game protocol, so it is not an abnormal occurrence, as reconnection is also used to handle overload for a given server. The storage nodes have a gossip protocol to identify which to which segments there was written a change when the segment was not supported as the primary segment. Each segment of the key space is either held in or marked as primary or secondary, and over time changes written to secondary are checked with the primary. For details, just look at the Dynamo paper. We just did as they did, because it seemed to work. To speed up this recovery, Dynamo proposes workload trees. We haven't implemented that yet. But it's on the agenda. Network splits are a lot easier to detect in the closed network that we propose for this. Reason being that while we think QuP techniques are nice, controlling your data is so vital for most commercial type game server vendors, service providers, that they'll never give out servers, so we do them as on a centralized space anyway. If a net split does happen and there's no clean cut whether who has the most changes and should be chosen as the right one, at some application level conciliation would be used. Vector clocks are there to help identify which changes have done where and whether it's missing. Again, that is not fully implemented yet. Some details on how this is done. Transactions are simply messages sent from the game servers to the storage servers, and each one sends not only the new value, but also the old value that it assumes to be correct. If that is not the case, the transaction or this message to that storage node will fail automatically, and as far as, or if at least the required number of messages or transactions are successful, then it reaches quorum. The design is a little bit sloppy there on purpose. There are no multi-object transactions supported, simply that for the simple reason that they're not used that often and would cause a lot of latency overhead with multi-step transaction or multi-step protocol needed. There are some specialized API calls to this storage node for doing set operations. That is very useful, for instance, in adding objects to auxiliary nodes without, while minimizing the update conditions. Client assignment is done by a separate system control service that also can do authentication of the user. And it is also informed of the center of the subtree that the client, that server holds, so that it can choose which servers ought to be applicable for a new connecting client, so that clients get that all clients in the same spatial locality within the virtual environment get assigned to the same server as long as the server is not overloaded. Okay. We tried this out. I've written a prototype in Erlang and have run it on a set of just 5 PC machines. For some bizarre budgeting reasons, we cannot use cloud providers like Amazon, So it has to be done on our own machines. We're currently setting up our own cloud infrastructure. It takes a lot of work, and I'd rather use Amazon, but that's public service for you. The way this works is we have the number of PCs. On each, there's one storage node running, because I thought, while I have more storage nodes, which just adds more overhead, but the number of server nodes within the QuP nomenclature, it's the QuP client. That's not the game client, but if the storage server is the server, then the game server is the client for this protocol. And assigned to each game server are a fixed number of 5 generators for changes that simulate an object moving an object moving around. And the number of game servers, so to speak, that is running on these 5 hardware PCs is continuously increased. And we measure the delay for movement, because this is all message-based. The actual moving, the client of the actual moving objects get the same state update information as all the others that are observing. So you observe yourself, and then by knowing that the move was successful, the client knows that you did actually move. This is the delay for 20 to 100 virtual machines. Game server type virtual machines running on these 5 PCs. Obviously, the delay in the 90th percentile is totally unacceptable. The point of this exercise was not to show that it is a viable running game system. It was more to get an idea on what the type of latency increase is for increasing the number of game servers in the system. Obviously, for actually running a valid game, you would need a lot more hardware resources. But as this does not, as the average does not go through the roof, even though it is unlimited hardware, we're pretty confident that the overhead of game servers talking to each other or talking to each other via the storage nodes is fairly acceptable. This basically led us to identifying a large number of parameters that we have to go through individually and check, most of which, or most important of which is the avatar density, the number of avatars in a given space that is still supported. Obviously, if a single server is overloaded, you get the situation where multiple servers handle basically the same space within the virtual environment, and then the effects of vision range on the latency. Most important is a complete check of error rates that are still acceptable for the system to continue to function. Same with update frequency, and for tuning the ratio of game servers to storage servers. The experiment was fixed simply because it didn't make sense to add storage servers. Okay. Our summary, it allows for a large number of server nodes that in turn should, with the necessary hardware requirements or hardware resources, support a large number of clients. A lot more work is needed to optimize this. This is definitely a work in progress. Check us out at www.qdoors.org. At the moment there isn't much there because I'd rather do code than websites. As far as the source code is concerned, let's talk about it. It will eventually go to GitHub, but I have to get some licensing and rights things cleaned up before I can put it there. Thank you.
So with you just now, it seems there is some similarities between what you're trying to do and also in the way you set up your system, and I think what Specs is trying to do. So Mahdi, I will be asking you to give some comment or ask some questions, but let's give Joachim opportunity.
I have many questions, but I will focus on one about the nimbus, that is the area of interest. So what happens when the nimbus gets crowded by 100 of avatars, or what happens when it gets empty? So does the user feel that it is alone? So I'm just wondering about this model of area of interest.
To ask the second first, yes. If it's empty, then the avatar is alone. If it gets crowded, step one, as long as all the other avatars that can perceive each other or are within this nimbus are on the same server, it basically just is happening within the cache and updates are forwarded. But the changes of one avatar are subscribed to by all the others, and the update is pushed out to the clients.
No, what I mean is that we're talking about the scalability. So at some point, your nimbus can be too crowded for scalability issues. I mean,
also, in principle, yes. If you place your observer right up at the root, you get the God mode problem, which is that you can observe everything that's happening in the whole virtual environment, and you break the scalability. Yes.
No, what I mean is the nimbus is some fixed size, or how it works? It's variable?
It's just where you, well, it usually is fixed by the game rules, but in QuP, it's just where you place your observer up.
So you can change so maybe you can see someone and this someone does not see you.
That would be an asymmetric nimbus setting, and yes, QuP would support that. Let's say, this is my observer, this is you, this is your observer. I cannot see you because you're in a, that's not quite as simple, but let me take this as an example. I cannot see you because you're further up in the tree.
Yeah.
That might mean that you are very large, that your avatar is very large, so I can't see you, because it's also intersecting with these areas. But it also might mean that you're in some corner where you can observe everything because your observer object is a lot higher on the tree, but I cannot observe you because basically your actions are not forwarded to my subtree.
And I think this is we're getting details here, which I think is more beneficial one-on-one. Mahdi, actually, sorry, I now will ask you not to ask a question, but because I want to continue to the next user. But I think there will be very fruitful discussions happening over coffee later. So